Welcome back. Flat Math 102. I want to thank everyone who viewed or commented on Flat Math 101. The intent of these videos is to get to a point of common knowledge so that we can move forward with what I really want to say. It just is too complicated at this point. So we're going to begin with vectors. We talked about velocity last time, and velocity has two components. It has the magnitude and direction. And the easiest way to visually represent velocity is with a vector. That is a line segment. A line segment has a defined length. That length is the magnitude. When we put an arrowhead on the end, now we have direction. This vector is a line segment with an arrowhead on the end. The two important points are how long it is and the direction it is pointing. This vector, if it turns, is no longer equal. It's not like similar triangles where it doesn't matter where they're pointed. It does matter where it's pointed. The most common way that we talk about vectors would be on our coordinate system, our XY coordinate system. So we might have a vector like this. How would you know if this vector is equal to another vector? It has to have the same length and be pointed in the same direction. So in this case, we would talk about this angle up off of the x-axis. Another way to talk about vectors and how they're used is in orienteering, north. So I'm going to take this same vector, try to copy it. So it has to be pointed the same direction, meaning parallel, and it has to be the same length, and I'm going to guess. So it looks something like this. We could describe this vector both visually, with it drawn on the system here, or with symbols. So in this case, this would be north, and then from due north, you turn east. I'm going to say that is 70 degrees. North, 70 degrees east. This vector describes a direction and a magnitude in the cardinal coordinate system. The most common way to talk about vectors, and the easiest, is what we call component form. So this looks kind of like an ordered pair. Well, it is. X-axis, y-axis. So I'm going to go in the x direction 3, in the y direction 2, and that gives me this point, connecting it with the origin, and there we have a vector. These braces tell us that it is a vector and not an ordered pair like 3, 2. 3, 2 would be this point right there. Now, what is important about vectors is we don't know where they start. We know the magnitude and the direction, but we don't know the position. So I could make an identical vector. Mathematically, they would be the same. Right there. And it actually is an important nuance that it doesn't matter where we write them. What's important, because when we get into some physics diagrams and some calculations, we need to separate apart a complex system, and we can do so with these vectors. Now, it's even easier to draw vectors with some graph paper. So we talked about the XY coordinate system, component form on a cardinal coordinate system, and this one will simply be like a treasure map. That says, go north, 70 degrees east, 2 paces. That might be too short. Then go south, 10 paces. And then go due west, 5 paces. We can do this with vectors. So wherever, it doesn't matter where we start, and that usually is the missing part about the treasure map. They tell you where to find the treasure, but not where to start. So we're going to go 2 paces, so that's going to be the length of 2 of these, in this direction. And this is going to be crude, and that's okay. So we're going to go 2 paces that way. Check. Now we're going to go 10 paces south. Well, if we went from here to there, this is where we currently are, and we need to go 10 south. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. We started here at our front door. We went 2 paces that way, 10 paces that way, and now 5 paces to the left, due west. 1, 2, 3, 4, 5. And hopefully, X marks the spot. So we use vectors to describe the direction we're going and how far we're going, or the direction of something and how powerful it is, or the direction of something, how fast it moves. But this entire system, if I were to connect these 3 vectors, I could pick it up and move it over here. So we don't know, generally, where they begin. We simply know where they go and how far they go. Next is a free body diagram, and we'll get back to the graph paper. All right. So a free body diagram in physics is the ability to break a system down into its components and look at each of them separately. So in this case, we have a mass A, a rope up over a pulley. We're going to assume it's a frictionless pulley, and then a mass B. They're connected by a rope. So I'm going to take A down here, and I'm going to enlarge it so we can talk just about it. This is A. And then over here, I'm going to enlarge B so that we can talk about it independently. Now A. A looks to be more massive. We're going to assume that. A has working on it the force of gravity, which I'm going to call G. And it has the force of the rope, which I'm going to call T. Mass B has the same thing, except if it is less massive than A, the force of gravity on it will also be less. And again, the direction is straight down, and the magnitude is represented by the length of the vector. But what is the same on both of these is if they're connected by a frictionless rope, the tension on this object, this direction, and the tension on this object, this direction, must be equal. Or they're not connected, or the rope is stretching or shrinking. So in this case, it looks like A is resting on the floor. If A was not resting on the floor, what would happen? The more massive A, now this is G sub B, G sub A, T sub A, T sub B. Now tension A equals tension B, but gravity on A and gravity on B, the forces are different because the force is equal to mass times acceleration. The masses are not equal. A is bigger. So the forces will not be equal. Moving over to where we really want to get is into net force. So I'm going to draw another component. We don't have to know where it came from. All we need to know is what forces are acting upon it. So I'm going to draw this object. It has a vector off here at a 45-degree angle, and that is something that's pulling on it, like a rope. It has straight down force of gravity, and we're also going to add friction. And friction is slowing it down. Now, in order to find the net force, so that is the force that's left after you add everything up. In order to find the net force, we're going to have to combine these. Well, how are we going to combine the force of the pulling plus the force of gravity plus the force of friction in order to equal our net force? If our net force is 0, it will stay put. Back to this example. If A is actually resting on the floor, then there is an additional force from the floor to make the gravities balance. For a system to be in equilibrium, the net forces have to be 0. They have to cancel out. So we want to add these 3 things up. How are we going to do it? Well, remember back to our orienteering. This is addition of vectors. It's going to be the same here. P is in this direction. G, straight down and a bit longer. F, straight backwards and pretty short. All right. When you look at this system, where did we begin? There. Where do we end? There. So back to the treasure map. Wouldn't it have been easier just to go straight from the start to the X, to the treasure? Well, of course, that'd be the easy way. And the point is that this route is the same as this route. You get to the same destination. So this allows us to separate out a complex physical diagram, break it into its components, and then sum up the forces acting upon it, and come up with a rather simple, if you start here and you head around the path, you'll end up at the destination. Now, if I measured the angle of the resultant vector, I could tell you exactly where this object is going to move. It's going to move in the direction of the red vector, and it's going to move at the magnitude of the red vector. So some of the pulling is canceled out by some of the gravity. Some of the pulling is canceled out by the friction. But the gravity is largely, its downward force is largely left alone, which leaves us with this vector, which looks to be sort of down and to the right at 45 degrees, something like that. How do we find the net force? Is we add up the forces. Combined in them, if they are vectors, their direction is already included. If we just had numbers, we would need to know which direction. And left versus right, on a coordinate system, we use negatives to talk about going to the left or going down, positive numbers for going to the right and going up. This will set us up nicely to be able to talk about rotational issues next time. Thank you for watching.